So today we're going to keep working in chapter 6, looking a little more closely at gas, liquid, equilibrium, and systems, starting to talk about Raoult's law, Henry's law, and looking at how we can identify for a mixture of gas and liquid component breakdowns for each phase. So give me a second. My system's being a little picky today. All right. So today we're going to look at single and multi-component gas liquid systems. If you've got your book, this is at least section 6.3 of the text that I have. Before I jump in, were there any questions on the first couple sections of chapter 6? I know last week we talked about phase diagrams and estimating the vapor pressure through various means. So you guys remember how we were able to find vapor pressure? Who can give me a method? We had quite a few that we had talked about.
We can use Antoine's equation.
All right, we had Antoine's equation. Right, and it had that log P star equals A minus B over T plus C. What other methods did we have?
The Cox chart.
Right, Cox charts. Can you give me a couple more? You guys are doing great. All right, I like that, Clausius. Clapeyron equation. Very good. All right, ln P star equals delta HV over RT plus B. One more. The last one was just the generic Clapeyron equation. Not nearly as common, but it is technically valid. My pen's getting a little creative today. All right, so we had all these different methods. Like I said, these constants, this is in, should be table B.3 in the back of the book. And The enthalpies of vaporization, I should probably tell you where that is in the book. Oh, let me correct that. This is before. And then the physical properties for the components, including the enthalpy of vaporization, is table B1. Very good job, guys. All right, so now let's talk about what to do with gas-liquid systems. Where we have one condensable component. And here I'll jump over. We can look at this example. If we have an air and liquid water at equilibrium at 65 degrees C in 1 atmosphere. So we have air and water. Now let's put some liquid water in the container. Temperature is 65 degrees Celsius. The pressure is 1 atmosphere. And how do we calculate the molar composition of air and water in the gas phase? And so we have to know some information about either air or water to solve this problem. Well, we have the temperature and pressure, and that should allow us to determine the vapor pressure of water. All right, so with the temperature, we can estimate the vapor pressure of water. But we need to know some information to find the composition, and that's where the pressure comes in. And so with the pressure, we can estimate the molar composition of water if we have the vapor pressure of water. Well, and the question is how? Well, this falls under the application of what's known as Raoult's law. And Raoult's law states that if a gas at a certain temperature, no, I hate when this happens. Temperature and pressure contains a saturated vapor with mole fraction Y
small.
then the vapor pressure of that component is the saturation pressure. If it's the only condensable component. If it is the only So mathematically, we can say the partial pressure of the substance is equal to the mole fraction of that substance times the total pressure. But if it's the only condensable component, we can say the vapor pressure is also equal to that saturation pressure. And so we can essentially use the pure component vapor pressure as the partial pressure. And that's an important thing to note. And with this information, we can calculate the vapor pressure of the water using Antoine's equation. And with the vapor pressure, we can estimate the mole fraction of water in the air. Because in the system that we have with air and water, water is the only condensable component. And so what we can do is look up the Antoine constants for water. And with that in mind, we can calculate the vapor pressure of water. So we have log P star equals A minus B over T plus C, where P star is in millimeters of mercury and T is in Celsius. And for water at 65 degrees, the A constant is about 7.96681. The B constant is 1668.21. And the C constant is about 228. So with that, we can calculate the vapor pressure of the water in that air-water mixture. So we have the log of P star equals 7.96681 minus B, which is 1668.21, divided by T, which in this problem was 65 degrees Celsius, plus C, which is 228. So that calculation should give you a pressure of, I believe, about 220 millimeters of mercury. Then we'll double check that real quick. Nope, I was off. 289 millimeters of mercury. And so using Raoult's law, we can say the partial pressure is equal to that vapor pressure. And here I'll put H2O to make it a little clearer. Which is equal to the mole fraction of water times the total pressure. Where the total pressure, like I said, was 1 atmosphere, and 1 atmosphere is 760 millimeters of mercury. And that tells me the mole fraction of the water in the air is simply that partial pressure or vapor pressure of water over the total pressure, or 289 millimeters of mercury over 760 millimeters of mercury. So that says the mole fraction of water in the air is about 0.38 or 38 mole percent. And that tells me that the mole fraction of air in that mixture is 1 minus the mole fraction of water, or 1 minus 0.38, or 0.62, or 62 mole percent. Dry air, or air. So let's do a quick recap. So when we're looking at gas liquid systems, and if we have one condensable component, we can state that Raoult's law applies, which allows us to estimate the partial pressure of a substance in a gas as the vapor pressure of that substance. And with that in mind, we can calculate the vapor pressure using one of the methods that we talked about earlier. In this case, we were looking at Antoine's equation because the constants are readily available. And with that Antoine's constants, we can calculate the vapor pressure of the water. And with that, we can estimate the mole fraction of the water in the mixture. And then from that, we can find the mole fraction of air in the air-water mixture. Are any questions of that? I shouldn't say, I'll rewrite this, the partial pressure. No questions? Let's look at one other example. So let's say a stream of air at 100 degrees C and 5,200 millimeters of mercury contains 10 volume percent water. So we're looking at this example next. And I said the temperature is 100 C, the pressure is 5,200 millimeters of mercury. So a couple questions that are here. It says calculate the dew point and calculate the percentage of vapor that condenses if the air is cooled to 80 C at constant pressure. And so it's, saying if we have the system that's coming in, 5,200 millimeters of mercury, 100 degrees C, if we cool the system down, we should lose some water out of the system, right? Because we have air and water in the vapor phase, and then air and water in this phase. right? So it's operating as a form of dehumidifier. And we have 10 volume percent of water coming in. So the mole fraction of air and water, 0.9 and 0.1. So then the question is, how do we find the dew point? Well, we have to ask ourselves, what is dew point? Well, the dew point is the temperature for a gas mixture, or even a pure component, so I won't say mixture, where the first droplet forms. So how do you think we can find the dew point? Any ideas?
What if we find our partial pressure of it coming in, or our partial pressure going out, and then use the table to find that temperature at the dew point?
I like that method. So can you tell me what the dew point is? I'm trying a little bit different way of lecturing today to see if I can get some more discussion happening. It's a little tricky. So in order for me to describe it, we know that the temperature coming in is 100 degrees C and 5,200 millimeters of mercury. And I'm asking to find the dew point, which probably tells me that this system currently isn't at the dew point. And so that indicates that at some point, the temperature needs to fall below 100 degrees Celsius to reach the dew point. And if the temperature is greater than the dew point, we're looking at what we call a superheated vapor. And that tells us that the partial pressure of our substance, which we already know is mole fraction times the total pressure, is less than the saturated pressure at that temperature. And so the dew point, which I'm going to say T sub dP, is the temperature where the partial pressure equals the saturation pressure at that specific temperature. So in order to find the dew point, we have to estimate our partial pressure. Then determine the temperature where that partial pressure equals the saturation pressure. So for this system, we have the total pressure, which is 5,200 millimeters of mercury. We have the mole fraction of water, which is 0.1. That tells us our partial pressure, which is Yi times P, is 520 millimeters of mercury. So the dew point temperature, is when the saturation pressure, which is 520. So we need to find the temperature where the saturation pressure is 520 millimeters of mercury. Does that make sense? So how can we find this temperature? Well, in the back of your book, I believe it's table B3. Are the vapor pressures of water versus temperatures in degrees C. As a function of mole fraction. Actually, it's not a function of mole fraction. I don't know why I wrote that. I apologize. So does any of you guys have the book? Are you guys able to see that table in the back? So the way this table works is you see how there's temperature Celsius on those first columns. And then after that, there's numbers 0.1, 0.2. That's its way of saying like negative 14.1, negative 14.5. And so what we're looking at is where that pressure is equal to 520. And so from this table, it's 520 somewhere between 89 degrees Celsius and 90 degrees Celsius. So to find the exact temperature, we would have to interpolate between 89 degrees, which is showing 506.1 millimeters of mercury, and 90 degrees, which is 525.76 millimeters of mercury. So when T is equal to 89 degrees, P star is equal to 506.1. And when T is equal to 90 degrees, P is equal to 525.76 millimeters of mercury.
On a test, if we had a question like this, would you like give us part of the table to look at?
I would probably give you a subsection of the table, yes. So I got a temperature about 87 degrees. Oh, excuse me. That was silly. 89.7 degrees. Might be 89.7 something, but we didn't have to be super picky about it. And so that's how we can estimate that dew point temperature. And if we're looking at something other than water, you're more than likely going to have to look up either a table similar to what's shown in the back in table B3, or find some equation approximation that gives you an idea of those vapor pressures versus temperatures. Is there any questions on finding that dew point? All right, let's take a look at the next part of this problem when we're looking at trying to figure out the percentage of water that condenses if we cool to 80 degrees Celsius, and then the final air composition once we know how much water vapor is going to condense. All right. So we know that the dew point is about 89.7 degrees. So as we move below that temperature, you're going to have more and more water condense and leave the gas phase. So the question then becomes, well, how much leaves the gas phase? How do I figure that out? Well, when the temperature is 80 degrees, the pressure, or that vapor pressure, is 355.1 millimeters of mercury. That means when that air system, the air-water system, falls to 80 degrees, that's the maximum vapor pressure. Anything beyond that has to fall out of that phase and into a liquid phase. Does that make sense? And so using Raoult's law again, since water is the only condensable component, if that system leaves at 80 degrees C and that pressure The mole fraction is that vapor pressure over the total pressure, or 355.1 millimeters of mercury over 5,200 millimeters of mercury. Which is 0.068. Excuse me, 0.0, yeah, it's 0.068 or 6.8 mole percent. So we went from 10 volume mole percent, whatever you want to call it, down to 6.8 mole percent. So now this becomes 0.068 and this becomes 0.932. And the difference between the two leaves as water, liquid water. And so so that's the final air composition. To find the percentage of water that leaves, right? There's a couple ways we can do this. We can take a basis of the feed and move on like that. Or we can just kind of do a quick calculation that says, well, if we had 0.1 coming in, 0.068 coming out out of 0.1, that should give us an idea of the percentage that condenses, which should be about 32%. Is there any questions on how I was able to do those calculations? Let's take a quick recap. So we were operating this as kind of a dehumidifier, where we're dropping the temperature of this stream of air and water coming in at 100 degrees C and 5,200 millimeters of mercury. And so we drop the temperature down, and once it's hit its dew point, water in the gas phase starts falling out of phase and becoming liquid. Then as we continue to cool beyond that dew point, more and more water will join the liquid phase. And so we could find that dew point based off of this equation here, trying to figure out for the partial pressure that we have, what temperature is essentially when that partial pressure equals the saturation pressure. Once the partial pressure equals saturation pressure, then liquid has to form. The air, so to speak, can no longer hold the water in the gas phase. Excuse me. And so that means we get water to condense. And looking up in the table for the pressure that we had and the vapor pressure that we had, we can figure out what's the dew point temperature. Once we have that, we can use the same table to get the saturation pressure for water at 80 degrees C. And knowing that, we can estimate, based on the total pressure in our system, the mole fraction of water. Now, when we're looking at air and water systems, there's a couple of terms that we like to use. One I'm sure you've heard of before is relative humidity, especially those of you that live in Mississippi, you know, humidity is kind of king during the summer. And what we're looking at when we talk about humidity, relative humidity, it's essentially a comparison between the partial pressure over the saturation pressure at the temperature in which the system exists. Which is kind of a way of saying, and at least I like to think about it is, you know, based on the amount of water in the air versus the maximum amount of water the air can hold at that temperature, right? Because the higher the temperature, the greater the capacity, or the higher the vapor pressure that the water can exert, and so more water will exist in the gas phase. As it cools, then the vapor pressure falls, and so the saturation pressure goes lower and lower. And so it's a comparison of the current water partial pressure versus its saturation pressure times 100. So if I say the relative humidity today is 60%, that implies that the current partial pressure is 60% of the saturation pressure at the outside temp. All right? And that's why, you know, it becomes miserable in the summer when the relative humidity is high, because your body is unable to vaporize water via sweating as effectively, because the air can't hold that water that your body is trying to give off, right? But the humidity is too high. So that rate of evaporation is slow, which means you feel hotter and it feels miserable. Let's look at another example that we can see here. Oh, apparently I can't count. It's example 3. So we have a gas tank which has 10 mole percent styrene and 90 mole percent of hydrocarbons that won't condense. Maybe it's methane. It's 100 degrees C and 1,000 millimeters of mercury. How can we calculate the dew point, the relative saturation, and the percent saturation of styrene if the vapor pressure is 200 millimeters of mercury at 100 degrees C? So let's look at this one. It's a little different, not working at water. So I've got a gas tank. It's got 10 mole percent styrene, 90 mole percent non-condensables, other stuff. The temperature, what did I have? 100 degrees C. And the pressure is 1,000 millimeters of mercury. And I said that the vapor pressure of styrene is what, 200 millimeters of mercury at 100 degrees C. So what is the dew point? Well, how can we find the dew point? What do you guys think? Well, the dew point for styrene is the temperature where the partial pressure is equal to the current, or the saturation pressure is equal to the current partial pressure. Right? We can look at the system now and say, well, we've got 10 mole percent of styrene, or Y sub S is 0.1. That indicates the partial pressure of styrene right now is 0.1 times 1,000 millimeters of mercury. Or the partial pressure of styrene is just 100 millimeters of mercury. And we know when the T is 100 C, the vapor saturation pressure is 200 millimeters of mercury. So that tells us we're still looking at a superheated vapor. And so we have to figure out at what temperature in this system, when the total pressure is 1,000 millimeters of mercury, would we see liquid formation? Well, the book doesn't have vaporization data for styrene. So we have to look it up. And so I'll give you guys this. If for styrene, the Antoine equation parameters for log of P is equal to A minus B over T plus C, where P is in bar and T is in Kelvin. A is equal to 4.0593. B is equal to 1,459.909. And C is equal to negative 59.551. How can we use the Antoine equation information I pulled? And this was from NIST, which stands for the National Institute of Standards and Technology. Their website's really good for finding parameters, and I recommend it. So how can I use this Antoine equation to find my dew point? You guys have any ideas? Well, if my pressure right now is 1,000 millimeters of mercury, that should correlate with bar. And so with that, I get about 1.33 bar. And my temperature was 100 degrees Celsius, which is 373 Kelvin. Right? But what I want to know is the temperature where the vapor pressure is the saturation pressure, or 100 millimeters of mercury, which is 0.13 bar. And so for this expression, I have log 0.13 bar equals 4.0593 minus 1,459.909 over my temperature, which is what I'm looking for, which is the dew point, minus 59.551. And so by using the Antoine's equation, knowing what I want my vapor pressure to be, the saturation pressure, I can solve for my dew point temperature. So this log 0.13 bar is about negative 0.876, which equals 4.0593 minus 1,459.909 over the dew point temperature minus 59.551. So what do I get for my dew point temperature? Keeping in mind this will give it to us in Kelvin. What do you guys think?
I got 235.7.
Okay. So 235.7. So 235.7 Kelvin is negative 37.3 degrees Celsius. That seems a little off. Let's see if we can check this one more time. This is a little tricky to do sometimes. Let me see what I can come up with.
I just did it again and I got 354.8. Maybe I was wrong.
All right. That sounds more what I was expecting. Yes, what you have now is correct. So we have 354.8, which is 81.8 degrees C. Yeah, that sounds right. But the method's right. And so now we have the dew point temperature. So then the question is, what is the relative saturation and the percentage saturation? Well, the relative saturation or relative humidity is the current pressure over the partial pressure, which the current vapor pressure we said was 100 millimeters of mercury, and the partial pressure at this current temperature was 200 millimeters of mercury. So the relative saturation was 0.5 or 50% relative humidity. Now, the last thing we're looking for is the percentage saturation or percentage humidity. Now, the percentage saturation is a ratio of the partial pressure to the saturation pressure, but it looks a little different. And here I'll use the, should be S sub R. I don't know why I like R sub S, but I'll use what the book uses. So the percentage saturation is the partial pressure relative to the system over the saturation, partial pressure, relative to the system. So for this problem, it would be 100 millimeters of mercury over the 1,000 minus 100 millimeters of mercury all over the 200 millimeters of mercury divided by 1,000 minus the 200 millimeters of mercury. Or it would be 100 divided by 900 divided by 200 over 800. And with that, we get about 0.44 or 44% in terms of percentage saturation. It's just another way of calculating things. More often than not, we deal with things in terms of relative saturation because it's more widely known and accepted. There's a couple other ways that you can do these things, like percentage saturation. There's also molar and absolute saturation. However, they're less common. All right. So I think that's a good place for us to stop. One thing I do want to note is that I'm going to have office hours today from about 2:30 to 4. I have a quick meeting at 2 that I can't miss. Also, I'm going to release the midterm solutions later today and trying to give you guys some more feedback about where you did well and where you messed up on your midterms. I was just trying to get grades out and the grades done last night because that's usually what people want to know first. But rest assured, I'm going to give you guys a little bit more feedback. Not as much as I'd like. I know everybody likes having their papers marked up. It's a little kind of difficult for me to do when everything's online. But I will provide you some feedbacks in terms of how I scored your midterms and let you look at solutions to kind of compare your work with my solution, so that hopefully that will help you prepare for the final. Are there any last minute questions, comments, concerns?
I have a question about the example you just did.
Sure.
So how do you get rid of a log? You do base 10, right?
Yeah, you do a base 10. All right. Well, then take care, guys. Have a great rest of your day.